In Todd Hilton's presentation yesterday, he mentioned two strategic approaches that we can take, trying to get some mileage out of, I should say engineering mileage out of understanding the brain. One is to look at the, paraphrasing here, look at the whole brain. And the second was to look at restricted functions of the brain. And this is an example of the second and maybe an argument for it. So map-seeking circuits started with, as an attempt to solve the correspondence, to find an efficient, robust solution to the correspondence problem in vision. Excuse me. Which probably most of you know what it is, and I will explain it for those who don't in a moment or two. And people know this has been a long search. And the assumption here was that the existence of a solution in the brain is an existence proof, and that if we use the constraints of neuronally plausible operations in data flow, it should be able to constrain the mathematical solution. And that was the approach that I took to coming up with a solution that you'll see. And the result was not just a mechanism for the correspondence problem, but a general method for solution of class of inverse problems that involve transformation discovery. So it actually turns out to be much more broadly applicable than what the original search was directed at. And as a byproduct, because of using the constraints of neuronal plausible operations in data flow, there was an analog circuit with neuron-like elements for implementing that solution, that method of solution, which is applicable not only to the correspondence problem, but turns out to inverse kinematics, root finding, puzzle solving, Rubik's Cube, very important applications, targeted stimulus delivery for vision research, and quite a few other applications which fall into that general class of inverse problems. So going back to vision, I'm not going to talk too much about the other problems, is the one that everybody is familiar with. If we have a model, 3D model of a pig, for example, and two images in which the pig appears, even small differences in the orientation or the viewpoint of the pig result in different appearances, and that can be quite radical depending upon the viewpoint. And this is the classic correspondence problem. How do you when you have a single object in different image formation transformations, how do you associate it? There's a little note down here that one of the processes that has been assumed to be important in vision is pre-segmentation of the image into separate objects. But it turns out that if you have transformation discovery, that segmentation is an emergent consequence. It doesn't have to be done as a separate step.
We just lost the screen.
Oh no.
Pop out? Okay, it's on.
It's back on? Okay, tell me if it goes off again, because this thing didn't screw in here. Oh. Now, people are probably familiar in the field that there's a lot of talk about invariance, and that the objective of a lot of neuronal models has been to address this problem of the difference in appearance of things by invariance. The solution to MSC is a transformation discovery mechanism, and this is an extremely important difference, because discovery means that it's a method that is aware of transformation and is able to report not just the identity of an object, but the parameters of the image formation and of the object transformations itself, like pose and change in morphology, articulation, and so on. Invariance is specifically designed to be blind to transformation and reports only object identity. So in this particular case, successful invariance would be blind to the fact that these two pigs are posed differently, and similarly with the cats and the car and so on. And psychophysics and common experience tells us that this essentially is the falsifying experiment. We don't need to look into the brain to know that that's not how it works, because we know that we're exquisitely sensitive to differences in pose and position and articulation, et cetera, et cetera. So this was the motivation to find a system that would actually report transformations, not be blind to them. So the idea is correspondence as a mathematical entity is a measure of how well an input pattern R matches some memory template W after R has been subjected to a sequence of transformations. So the idea is that the image formation and object transformations, the morphology and so on, are decomposable, and that there's a method to discover what those transformations are, that sequence of transformation that accurately maps R to W. So what MSC solves mathematically is simply it finds the parameters of a set of transformations, a sequence of transformations, and if you have more than one template in a set of templates, it also treats those in effect as a transformation and solves for which template among, that is the W among the set big W, and the sequence of transformations that map R to the specific W in the set big W. So it's an optimization technique. So we have two kinds of transformations, as I said, that we're dealing with. We have the image formation ones, which is where in the image it is, the distance, orientation, occlusion, and so on. And then on the right, you have object configuration, which is that for human figures, you have not only the shape of the body, the pose, the articulation of the limbs of the body, but also clothes can transform the same figure quite dramatically. So all of these need to be accommodated and can be treated as a sequence of transformations. So the sources of bio-inspired computational hardware, in ideal circumstances, we could just reverse engineer. We would know enough about the brain to directly reverse engineer it. But I think this is highly unlikely, and I refer you to Christoph Koch's presentation here last year to make that argument cogently. So instead, we sort of have to go from hints by reverse engineering from multiple available constraints. And I would say the number one constraint, which I think is unaddressed typically, is functionality in psychophysics. That is, we know an awful lot about what vision does, and there's a tendency to somewhat ignore it if the method that we're using doesn't correspond to what the psychophysics and common sense tells us vision does. Now so that I would say is the strictest set of constraints. The second is neuroanatomy and neurophysiology. And we know something. A lot of the results are ambiguous. It's difficult to, as we all know, very difficult to build a system off that, but still we can get some ideas. And the other is that the neuron itself limits the set of operations that we can use to perform this computation. So if we establish a set of plausible computational repertoires, it has to be within that set to the solution. Now, in terms of functionality in psychophysics, often we ignore the ones that are not convenient. And one of the ones that was pointed out actually at another workshop that was run by the Army Night Vision Lab is that for military applications, the most important characteristic of a vision system is ability to recognize at a distance and very low resolution. And they've studied this extensively. And for humans, it's 4 to 8 cycles on the long axis of an object gives adequate ability to identify the class of the object. So this is one of the objectives that a method has to work and perform this in order to have this characteristic in order to be conform to what the human visual system does. And this has been studied, and it turns out that the target size is the dominant factor in filter type, object detector performance, and basically they don't work. You can refer to this publication, recent publication. The neuroanatomy and neurophysiology, well, we all know it. We took ventral stream, dorsal stream. The important point from the perspective of what I've done here is that the bidirectional data paths are used extensively. And in fact, there are more top-down than bottom-up pathways what I will show you has an equal number, but actually subsequent to this presentation, there's development that actually ends up with more top-down than bottom-up pathways. And there's inter-area connectivity patterns from Angelucci and et cetera, but again, not important at this point. What is important is the computational repertoire of the neuron. And because this also translates into what you can do neuromorphically. So what I'm going to show you has only basically 4 basic functions. There's combination, which is a kind of a monotonic function of the sum of signals. It does not have to be linear, just has to be monotonic. Gating of one signal by another, and I refer you to Bartlett-Mell, as this is an intra-dendritic function. It's quite a few years now that lots of evidence has been found about that. Mapping, of course, is just a matter of connectivity, and inhibition, which we all know, attenuation of one signal by another. And the point is that taking those 4 functions, we can get weighted superpositions, we can get matching operation like a dot product or more sophisticated matching functions, we can get geometric transforms, and we can get competition. And what I'm going to show you simply uses those 4 operations to find solutions. The crux of the correspondence problem, why it's always been a problem, of course, is the combinatorial explosion. So if you take a typical image and 30 scalings, 30 rotations, 30 azimuth and 30 elevation rotations, you've got a space of 10 to the 10th possible distinct transformations, not tractable. So the usual machine vision suspect for doing this is SIFT plus RANSAC plus the fundamental matrix, which is that you find a few features using SIFT, you sort them through them, you reduce the set using RANSAC, and then you find a consistent projection using the fundamental matrix. And this works well on certain classes of problems, but unfortunately on typical military problems it does not work very well. And here's just an example where in the lower left-hand corner it's just an extract from the image, and what SIFT finds as corresponding points is very nice if you take the exact patch from the image and has the same background. But if you simply erase the background, now SIFT finds more correspondence between the skyline and the target than between the target and the target. So this is well known by people who've used this, so it really doesn't work. The other thing is it's not plausible for a neuronal solution because of the computations involved in the fundamental matrix. So how does MSC solve it? So if we think about this problem, if we've got a bunch of objects in the input image and we've got a memory template and there's some transformation in the input image for the A, we want to match the A to the A. We have, just by the translation, pixel by pixel translations and rotations, we have 10 million combinations, not viable. However, if we could simply decompose this into the sum of the transformations, 380 plus 380 plus 72, we'd have only 832 combinations to search instead of 10 million. If we can apply the transformations to superpositions of the transforms at each stage instead of to them individually, that is, in brute force. So what I mean by superpositions is if we take a number of transformations of the in the x-axis and create a superposition of them, and then apply to that superposition translations in the vertical axis, and then take rotations of that superposition of those, we notice that in one of the resultant superpositions there's actually a match. But the problem is which sequence of transformations got us to that. We don't know that. All we've done is essentially created a grand superposition of all of the possibilities and found that there's a match somewhere in there. So that's one problem, is that we know that the visual system reports transformations and this doesn't. The other problem with this is that in practice, this only works on that first match maybe a third or a quarter of the time, and the smaller and more background there is in the input image, the less likely it is to work. This is a solvable problem. We use the characteristic of the visual system that there is transformation and pattern, that there is data flow in both directions, bottom up and top down, and competition, and an ordering property of superpositions, and now we can actually quickly converge using those to a correct solution. So the essential issue here is that if you have a pattern with a sequence of transformations in the forward direction, there's an inverse sequence of transformations that at each stage creates a match between, at any stage there is somewhere there's a match in the transformation. And that bidirectional flow gives us an opportunity to do matching for each stage of transformation. So I'm quickly going to go through this. By the way, if people are interested in this is all described much more in detail online, and I want to get to the neuronal circuit, but you have to understand this basic principle. So the principle is that you create superpositions of all of the transformations in the backward path. It sits there waiting for an input, and then using a correlation and a gating of each of the contributors to the superposition, you can create a convergence that selects it, and I'll just show you quickly the mechanism. So the Q's represent the degree of match between a particular transformation and the appropriate backward path, the transformation of the forward path, and the transformation and the superposition in the backward path. And that Q affects the convergence of the G's, which affects how much each one of the transformations contributes to the superposition. So you can see as the convergence evolves that the poorer matches get removed gradually by a change in the G coefficients until only the correct sequence remains as the final state of the convergence. And that is the correct sequence of transformations from the input image to the memory template. So the correct X translation, the correct Y translation, and the correct rotation. So the circuit and the algorithm looks like this, and the math expression of it in algorithmic form is that each stage a superposition is computed, superposition is computed of the memory templates, which in this stage, and at each stage of transformation on the backward path, and the same kind of operation on the forward path, except on the backward path, of course, we've got the inverse transformation to the forward path, where there's one that corresponds to each one. Each transformation and its inverse are gated by the same G coefficient, and this proceeds in the forward direction, and then there's a computation of the match at each stage of transformation for each transformation, and that's what steers those Q's, which are the degree of match, steers the convergence. And then a simple competition function gradually changes the G's to change the contribution to the superpositions as you saw. So this is all of the math. This is the whole thing. This is the whole algorithm. And what's important here is you'll notice that there is only one tunable parameter, which is the rate of the convergence. Everything else, all the behavior, is determined by the structure, the connectivity, but not by any kind of tuning. So from an engineering point of view, this is a vast simplification over a system that requires a tremendous amount of training. This is all analytically constructed. Now, the other point about this particular K parameter is that there's really only a threshold below which, that is, it always converges to the same result. So you can converge too fast and you'll get lower accuracy or less percentage of correct solutions, but below a certain speed, the convergence always is to the same solution. So it's a very insensitive parameter. So an MSC system, map-seeking circuit system, is this MSC which finds a sequence of transformations, and you have to take an input image and convert it to a representation which the MSC can use, and that's typically a sparse representation like edges. And then you take the model on the other side and convert it to the same. So the forward path gets the input image representation, the backward path gets the representation from the model, and then the MSC outputs a number of parameters, which are the parameters of the transformations, and that is used for validation if for some reason you don't trust the result at the MSC and you want to validate in a real system. That's typical. But what I will show you is results that are unvalidated. So here's a typical situation. Again, back to the pig and the 3D model. So the model is a surface normal 3D model of the pig. The image contains the various things. And you can see from this convergence, we're looking at now at this particular point where the marker is in the 3D to 2D projection. It starts out with a superposition of all of the 3D to 2D projections, and it converges, as you can see, to the correct pose of the pig. Equally important, if we follow all this path all the way up, we get all the way to the correct scale, rotation, and translation. So if we multiply the input image by what comes up the backward path, we get the segmentation that I was talking about earlier. So in the convergence, you can see it has isolated the pig from the background. Again, an emergent property of finding the transformations. And quite simply, if you have two different input images with the same model, it converges to one view. Just change the view, the input image, and it converges to the other view. Has no problem with crowded targets because we're not looking for features within the object, but the object is the shape of the object. In this case, it's occluding contour. So here's the 3D model that is used, and it finds both cases has no problem identifying the particular object from ones that are actually quite similar. Natural environments, not a problem. Again, this is a Fort Baker data set. The models are 3D models of the tanks, and the correct orientation, scale, location are found. Distinguishing similar targets, not a problem. At APL, at Johns Hopkins Applied Physics Lab, they've used the algorithm completely independent from me to work on synthetic aperture data, get very nice results. They also do EO. There's been results from Lockheed, have even extended to HRR. Again, some extraordinary results I unfortunately can't tell you about. The other thing that is really important is that MSC is mathematically rigorous. It is understood how it works. There's publications that I will give you references to. And method and its performance is analyzable. That is, you can predict for a given set of kinds of transformations that are implemented, and the nature of the signal-to-noise ratio or signal-to-background or distractor ratio of the images, the percentage of the probability of correct solution is predictable. There's a paper on the site that you can get that deals with it. It is based on this algebraic equivalence of the computation of the cues via the MSC and via what's called a correspondence terrain, where we take all of the correspondences as I defined them earlier, the sequence of transformations in R to W, takes R to W, and analyze this in a brute force way. This can be simulated to see what the performance is going to be, and then of course for efficiency you use the MSC computation. Anyway, you can see here's the simulation for a particular problem that I will show you, and you can see all of the yellow are the percentage of the probability of correct solution. The important parameters here is the signal-to-noise ratio, or the non-target ratio here. So this means that the distractors have the 9/10 of the amplitude correspondence of the target, and as the ratio, the signal-to-noise ratio increases as you go down this column, obviously. And I'm sorry, there's one other, this population threshold, which is essentially the number of locations at which in an image at which you have correspondences. And based on those two parameters, you can predict what the performance is going to be. And as you can see, as the signal-to-noise ratio increases, obviously you can have more and more density in the image and still stay up at the over 90% correct solutions. And this corresponds very directly to real results. This is the vivid data set and the EO data set, the IR data set. All of these are treated as independent images. Basically, a pickup truck 3D model in this wooded environment. And the data for this, and just again, the bright outline here is the back projected occluding contour of the model. showing that we've got a correct solution, that it fits even in the case here where there's some occlusion. So the summary of the data here is that we get, with no occlusions or small occlusions on that data, 92.6% correct. 2% of them, or 3.7% are alignment error, that is, it found the correct location but didn't get a correct transformation, and the false positives are 3.7%. If you go to large occlusions, which is like a third or a half of the thing is missing. With this particular matching function, the performance drops dramatically. That is predictable by the same kind of analysis. Oops. Hello. Sorry about that. Same kind of analysis that was done in this slide. Again, it's in a paper online. You can get a technical report. This was subjected to a little earlier version, to extensive testing by a major defense contractor. The data set here, again, that I can't show you because it's FOUO, but the setup was that a camera is flown over towards a set of military targets from about 1.5 kilometers out, and there's a sequence of images of those targets as it flies in. It's flown at about an altitude of about 70 meters. At 1.5 kilometers, there's about 4 cycles of resolution on the target, and we still got 5 out of the 7 of the known targets correct. By the time we're down to 430 meters, we're doing a 92.3%. It missed 1 at 330. The field was smaller, so there were fewer targets in the field of view. And as we get closer and closer, of course, the field of target, in each case it missed 1. Of course, that means 75%. Doesn't look so good. And then at the 75 meter is 100%. So again, this is another independent test, not where I'm choosing the data, but where contractors using their standard tests for this. And I should say, on the basis of that, they've decided to start marketing MSC as an ATR solution. Again, I mentioned that because it's transformation discovery, MSC is useful for finding inverse kinematics of many stages. In other words, beyond where there are closed form solutions. It's extremely efficient and also inherently very good at finding solutions around obstacles, as you can see here. I can't spend the time to go into it, but the point is that the ability to solve the inverse kinematics can be merged with the image transformation to find articulations of, solutions for articulated objects. So you can see here in the lower right-hand corner, you've got an articulated skeleton, which is solved by inverse kinematics. It's then morphed out to a standard figure just by a fixed mapping, and then morphed by a variable mapping out to match the actual contours of the input figure. So there's a variable mapping stage here, a fixed mapping stage here, and of course all of the mappings involved in finding the correct pose. And as you can see here, it is good at this is to the right are the solutions to interpreting this pose. And these are 3 different views of the same solution, so you can see it's a correct 3D solution. This was work done under an AFRL sensors SBIR phase 1 and phase 2. Articulated objects like tanks, that was done under the phase 1. Other things like roads, which can be represented as an articulated model, solves that perfectly well. Reconstruction, so on. Now we're getting to the point that, now that you know what MSC does, we can get on to the point that this is the object of this discussion, which is that there is an analog neuromorphic implementation that does this. Important point of this is the neural code representation. The critical thing here to consider is that the representation has to accommodate the range of values that the algorithm can produce. And in this particular case, when you have superpositions of tens, hundreds, thousands of things, the range of amplitudes can be huge, which is fine if you have a floating point processor, but if you have analog, of course, it becomes either it has to be compressed into a tiny amplitude range, or well, basically you can't handle it. The thing saturates and it can't distinguish between one superposition and another. So instead of using amplitudes, we represent it with phase or temporal coding, which means that the signal corresponds to the greater the amplitude, the greater the magnitude of the signal. And, oops, hello. So a circuit using this has some very nice characteristics. First of all, it's self-normalizing because the first signal to arrive essentially is the 1.0, and all other signals can be manipulated relative to that first arriving signal. So we can see here, for example, this is a recording from a simulation of a working MSC, where we can see that a competition has essentially taken multiple signals and weeded out the correct one. I'll show you this in a little more detail. But this graph basically just shows you the basic function. This is from a T-SPICE simulation where the lag between the small voltage difference is much smaller than the lag between this is the bottom again, is the time, between the larger variation. And the whole circuit works on this temporal coding principle. The basic cell is a very simple thing. It simply computes essentially dot products divided by or with an inhibition that is either subtractive or divisive. I'm not going to spend much time, but this is fairly obvious. And everything is built of these particular cells. So the neuromorphic system that does exactly what I was just showing you looks like this. This is a little confusing, but basically there are forward and backward paths that are paired up. There are cells that compute matches and cells that gate from one to another, which implement the transformations. I will show you that. And a bunch of circuitry that implements the competition. So corresponding to each one of these elements in the circuit, there is the algorithm that I showed you, or elements of the algorithm that I showed you earlier. Now, we're not claiming that the math is exact, that the circuit version is an exact implementation of the algorithmic version. What is important is that there is a monotonic mapping from any one of the functions in the algorithmic version to what is implemented in the circuit. So the same basic mathematics apply because this thing operates on the principle of ordering and not on amplitude, or I should say not on absolute differences, but simply ordering differences. And so the same analysis basically applies to the neuromorphic chip or the neuromorphic implementation as it does to the algorithmic one. So the basic circuit detail, the part that I would like to point out, is that in this mesh, if you like to think about it as in a way you can think about it as, I'll just go to the details here. So this is the flow of through the forward path, and the forward path is gated from one stage is gated onto the next by a cell which controls the G for each transformation. So when this is high, you get a transfer signal from the forward path and one layer to the forward path and the next. It also controls the backward path from the lower layer, from the next layer, I should say, to the previous layer in the backward path. So the same G controls the gating back and forth. The gating, the dot product essentially sums the match between the forward signal in each the forward signal and the backward signal and computes the Q. And so that's really all there is to it. None of these synapses have memory. They're all essentially dynamic gating. So you can think of this, if you think in terms of hardware logic, you can think of these as kind of analog AND gates, if you like. And this is an AND gate that computes a product and then sums non-linearly, but sums on the dendrite as does this. So the circuit has very few basic elements, again, going back to just those 4 operations that I described earlier. The neuronal expense of this is actually quite low. So for the target recognition MSC would take about 750K neurons if it has a single edge-only representation, and about 1.9 million neurons if it had 4 channels of orientation. This has been simulated in CMOS up to, I should say, a small section of this. This is done actually about 15 years ago with an AMI device, one micron device library. The dynamics, so there were two simulations. One was a large-scale simulation, which was more abstract, and the SPICE simulation to show that this could be built with real semiconductors. Again, this is not biologically realistic to the extent that it's a point process, that essentially propagation is instantaneous relative to cycle time, because the cycle time is about, in this simulation, is about a half megahertz. But that's really where it diverges most from realism, but it's actually very convenient from the point of view of building a neuromorphic circuit. I'll show you why. So here are other simulations. By the way, this can all be found in the book from Stanford Press. I'll give you the name of it and the description. There are no other publications on the circuit other than in that book. But this is what this is showing you is a tracking, independent frame tracking. We have this target, which is an outline of a jet moving through against the background, and you can see that the cells that record where its position are being identified. This is a 3D version of the convergence process where many cells identifying location are active, and then it converges each time to a single location. So this is all done with a large-scale neuronal simulation. Again, this was all done 15 years ago on a cluster. It's all described, including the simulations in the appendix of the book. This is map-seeking circuits and visual cognition. I'll give you the reference. Again, the references are online. And this is what the convergence looks like. There are 25 memories, which are different rotations of the target and a distractor target, or I should say distractor template. And it converges in few cycles, in each case, with each separate frame, relatively few cycles to a correct solution. So again, this shows the dynamic of the essentially oscillatory dynamics of this circuit. I wish I had more time to go into the details of this, but I'm probably pushing my luck here. All right, okay. So the question is, why do this? Okay, so let me describe for example, in the target recognition for the defense contractor or the Vivid, this is now implemented on a GPU, and the convergence time for the MSC is about 25 milliseconds on the Titan. And actually, that could be optimized probably down to under 20 milliseconds. So that's fast enough for frame rate. So why would anybody bother, given that, to do a neuromorphic implementation? Well, part of it is, if you look at NVIDIA's roadmap, they're promising over the next 2 generations 2 reductions in power by a factor of 2, if they're lucky. So the current 250 watts may go down in 2 generations to 67 watts. Based on the increase in performance from the last generation to this generation, which was not all that great, frankly, we might see it go down from 25 milliseconds to 15 milliseconds. Okay, so what would happen? We could do this in an FPGA, but actually, because of the memory bandwidth, the kind of application is limited. In fact, we just got funding to do this for that cone-targeted stimulus delivery, but that's a separate issue. Won't really, if it's not going to be big enough with the next generation of FPGAs to do it for the target recognition. However, if we were to make a 4-layer architecture with a 512 by 512 input, a 128 by 128 memory, with the transformations that are implemented on that, for example, in that Vivid, the pickup truck example, we would have 250 million transistors to do that in a 3 or 4 layer, possibly in a stacked architecture with 32K via connects. The power, if you assume 20 nanoamps per transistor max, would probably be under a watt peak, because we're typically talking about less than 1% average cells conducting and 10% peak at the beginning of convergence. At 1 megahertz, this would take 12 microseconds to converge versus, let's say, 15 or optimistically 12 milliseconds. So we've got 3 orders of magnitude in performance, and over two orders of magnitude in power reduction going to the neuromorphic implementation. And that's the argument for it, because a lot of the interest in this is to go onto UAVs and so on for target recognition, and 250 watts means a very big UAV. So basically, the summary of this is that we've got a working, efficient, tested algorithm for object recognition. It solves the transformation discovery problem, the correspondence problem. It solves the low resolution recognition problem, i.e. recognition at a distance. It's verified by multiple independent implementations, APL, Lockheed, Berkeley, others did it completely without my involvement. So they're just basically going from the documentation to their own application. There's one in production service where I'm not supposed to mention. It's inherently massively fine-grained parallel. The basic elements for analog implementation exist. Don't have to invent anything. There's a known engineering path to neuromorphic realization, and there's no new science to be discovered. It's an engineering project to take it from where it is to a neuromorphic implementation. So if you are interested, there's nothing on the analog circuit on this site, but there's a extensive discussion about how to implement from the algorithmic point of view at this website, technical reports, and so on. I'm done.
Time for a question as the next speaker, Stan Williams, is set up.
Oh, this looks really wonderful and exciting. And I want to read whatever book those chapters were from. Is that on that website?
The book is on the webpage. I think you can probably still get it. It's still, Stanford Press is still got stock, and you can get it through Amazon.
But actually, that's not my question. Can I get it without paying Amazon? That's not my question either.
I'm sorry, say the what?
Can I get it without paying Amazon?
Without paying Amazon? No, I can't give it to you because that would make the Stanford Press really unhappy.
Okay, so here's the real question.
Again, if you were interested just in the algorithm, all that stuff is on the website, and it goes way beyond what was published in the book, which is 2002. The circuit, this is actually the first time I've gotten to present the circuit to anybody since this thing came out. So this has been really a treat because I've been longing to do this. But unfortunately, it's in the book only at this point.
So here's the real question. In terms of either practical vision or human vision, there's two problems I didn't quite see solved with this. One is that if you have multiple instances in the input image of exactly the same object.
What happened?
And the other problem is...
Let me address that.
Well, let me give them to you both and then sit down.
Yeah.
The other problem is that if you have multiple different templates, do you have a way of doing them all simultaneously, or do you simply set up multiple different recognizers?
Okay, so what happens if there's multiple instances of the same object in the image, you can see what will happen is it'll converge. The first stage of the convergence is the G's in the translation layer corresponding to where all of the occurrences will remain at high values, and all the other locations will go to zero. This is demonstrated in the book, but it's called repeated pattern. Right? Essentially, it's a psychophysical behavior. We're very good at picking up repeated patterns of things, and this has so the first phase of the convergence identifies all the locations. If you keep converging it, it'll take the best one or one at random and focus on that one. But what happens is in the neuromorphic circuit, it now erases that one based on the backward projection to exactly that location. You let it reconverge and it finds the next one, the next one, the next one, the next one, the next one. So you can either find them all at once by stopping the convergence, or you can find them sequentially. Repeat the second question.
What happens if you have multiple templates?
Templates are selected exactly the same way as multiple transformations, and if you think of it from a mathematical point of view, if I just had a single pixel in the...
You're trying to recognize a library of different objects.
Yes, you can have multiple templates. That's inherent in the behavior. You can have multiple different templates in the converging concurrently. It selects the template as well as the transformation from the template to the object. So if there are multiple templates, it just selects, if there let's say you had multiple objects in the image for which you had multiple templates, it'll choose one of those and find the transformation to take it to that particular object in the image. It then erases that one based on the backward projection. You reconverge it again, it now finds another template that matches something else. So you can have multiple templates, and it's been demonstrated many times.